What we did is we set up the detector in a room where we expected to find radon. How we expect to find radon is there's concrete in the room, and if there's a crack, radon comes from the ground. It's the decay of uranium, and so basically we put the radon detector anywhere near a crack, and if it picked up some radon, we would get it on our readings. Basically, this is our radon detector. We just hold it in here. We make sure that it's not obstructed so that air can come in. And this is the little device that we made, if we can call it a device. It's basically just a pipe held with a string. And on the other side, we have a fan plug. Level dangerous is around 200 becquerel, and we got everything was from 40, we got a 60 peak. Instead of leaving it over a crack or leaving it just unattended, we put a fan with a computer, and basically it's pumping the air, and it's putting a flow. There's a flow of radon going constantly onto the detector, and we expect to see either more radon or less if there's no radon in the room.
Before, what we were doing is that we sort of planted our detector sort of in the middle of the room, and we would get sort of like a random reading of all the radon that could possibly be in the room. What happened when we changed it and put the fan to it is that now we're really getting, it's not as random as it was before, because we're really directing airflow to go there. For the radon group, one of the things that we were trying to do is actually try to model the situation using mathematical models. So it's not the easiest thing to do, but in my math course we're learning techniques and sort of ways to approach problems like these. So I guess it was just nice to see a sort of correlation between this research and one of my math courses. So here what I've been doing is basically any chain reaction is one where you start with something and then it turns into something else, and then that turns into something else, and then dot, 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 dot. Like here I just wrote that it changes 3 times, but it could change as many times as you want. So one of the challenges of doing it this way is that if we want to do it in general, let's say there's an n number, where n is any number, it's just that it's like this, you're adding a layer of abstraction that's sort of hard to work with. So it's sort of mind-numbing at times. So the idea of what we're doing here is that because we know how it's going to, like, what sequence it's going to decay by, we can sort of, using theoretical knowledge that we know about the system, we could actually try to predict what the system's going to be like at any given moment. Because it's very easy to solve like just one of them and then go like, okay, this is what's going to happen with this one. But what the challenge is that I want to solve all of them at once and have it in this convenient little bracket notation. And that is not at all easy to do with these math. It starts from a principle in physics called the radioactive decay law, which is this one here. The rate at which radioactive substance decays depends on how much of the substance you have. So if you have 1 kilogram, it's going to decay a lot faster than if you just had like a handful. So that's pretty much the gist of that. And the second part is that if you have a chain reaction, then if this one's decaying into that one, then the rate at which this one gets made depends on the last one. So I'm sort of combining this equation with what I know about chain reactions. And what I'm getting is that for any radioactive substance in a decay chain, it depends on the one before it. So if I is the ith one, then I minus 1 is the one before it. And and the amount that it's disappearing depends on how much of it is there. So this is basically just this really concise mathematical way of writing what we know about this. If I start with 10 grams of radon, how much of it am I going to have in 10 minutes, 20 minutes, 30 minutes? Well, like, you could figure that out. And that's a big challenge.
Basically, radon decays into progenies, and if we can have a fixed amount of the last stable progeny, which I think is lead.
Yeah, the last one is lead.
So what we could do is, if we know how much lead there is, what concentration of lead there is, we're trying to like do the reverse and find how much radon is coming into the room at any time. So we're trying to get models that are more and more accurate to get the decay, and then reverse it and get this. This is really physics and the decay of particles, and this is the one that interests me the most. Also had to do with science and health, and I like that too. So I just gathered what I like, because this is a cause of lung cancer.